What's up, guys? It's Mr. Bringle, and today we're going to be talking about how to now add math into our free body diagrams, our net force equations, which we also call the sum of the forces analysis. And now we'll actually be able to calculate some of the values just given minor details, really. So let's just kind of jump into this first one and we'll learn as we go. So, this first problem here says the mass of a grocery bag is 0.3 kilograms. There's some groceries in the bag. The bag sits motionless on the countertop. Number one, draw a free body diagram for the grocery bag. Perform a sum of the forces analysis for the vertical forces. Calculate the weight of the grocery bag. Determine the value of the normal force acting on the grocery bag. I do just want to kind of say this is, I've kind of changed this term over the years. Probably need to change it on this worksheet, but the sum of the forces analysis is the same thing as a net force equation, is what I refer to as a net force equation in class. So just kind of keep that in mind. So let's go ahead and just draw a quick. So here's a grocery bag. It's got some groceries in it, whatever. It's sitting on a table. Look at that. Weren't expecting to go to art class today, were you? So we've got our grocery bag here. Actually, that leg is way too long, and it's got some stuff in it sitting on the table. Right now, if we were to draw a free body diagram for this, I would go ahead and draw my X and Y axis here, and I will just go ahead and do this. We've got the weight of the grocery bag pointed down and the normal force, which is pointed up, and these must be balanced because the bag is sitting still. And this is really all we need. We have no horizontal forces here. We are now going to go ahead and write a net force equation, and then we're going to use the information that the problem gave us to actually solve for what it's asked us to solve for. So the first thing here is that the sum of the forces, which is what that symbol means, in the vertical direction, we're going to set that equal to 0. And we've talked about this plenty at this point, but when the forces are balanced, then you cannot say that they're unbalanced. So in this situation, we would say the net force is equal to 0. So just remember, this is another way of saying net force. So the F net is equal to 0. Now, I want to actually add in the forces in play here. So the normal force, which is pointed up, minus the weight of the bag, which is pointed down, must be equal to 0. And then if we add Fg to both sides, we can see that the normal force must be equal to the weight of the bag, which you knew, but this is mathematically proving it. Now, one thing that we've talked about, but we haven't had to really use, is that weight is equal to mass times acceleration due to gravity. That comes into play here because it's given me the mass of the grocery bag, right? The mass of the grocery bag is 0.3 kilograms. So I don't know what the weight of the bag is right now, but if I have the mass, I can figure out the weight of the bag. And since I know that the weight of the bag is equal to the normal force based on the equation we just wrote, I can then figure out the normal force. So let's go ahead and sub that in here. And we'll say, okay, well, Fn is equal to, instead of Fg, how about mass times acceleration due to gravity? And in fact, I am going to take this and we're just actually going to move this up here and we will continue. So I'm going to kind of draw an arrow up here. Okay. So this is being replaced with this. Okay. So now normal force is equal to 0.3 kilograms multiplied by the acceleration due to gravity, which remember is always 10 meters per second squared. And then we can find out that Fn, which is equal to the weight of the bag, is equal to this right here, 0.3 times 10, which would simply be 3 newtons. So what I've found here is that the weight of the bag is 3 newtons, and because the weight of the bag is balanced by the normal force from the table acting on the bag, I know that if the weight is 3 newtons, then the normal force must also be 3 newtons. Okay. Now let's do one that has some horizontal forces as well. Okay. So it says a box is being pushed across the floor at a constant speed. It says the mass of the box is 0.5 kilograms and it's being pushed horizontally with a force of 2.4 newtons. Okay. Actually gonna let me redo that there. Okay, force of 2.4 newtons, and that is being pushed. So that kind of helps us figure out what force that is. We're going to draw the free body diagram. We are going to perform some of the forces analysis or write out a net force equation for both the vertical and the horizontal forces. We're going to need to calculate the weight of the box, determine the normal force acting on the box, and then take it a step further and figure out the frictional force acting on the box. So for this one here, let's go ahead and let's draw our free body diagram. Here's a quick picture. Here's the box. We'll say it's being pushed to the right, and here's me pushing the box this way. Okay. And it does say at constant speed, so that's kind of crucial to drawing our free body diagram here. I will go ahead and draw out my x-axis, my y-axis, get my center of mass in there, get off of my line tool, right? And we know that we have obviously the weight of the box here. The normal force pointed up this direction. These must be equal. And then we've got my applied force. Please ignore my horribly drawn lines. My applied force this direction. And because it's moving at a constant speed, I know that the frictional force must be equal to the applied force. Don't bother with the amount of quality marks on there, just trying to show you that vertical forces are equal and opposite and horizontal forces are equal and opposite. So now we'll start with our sum of the forces or our net force equation in the vertical direction. So sum of the forces in the vertical direction are going to be equal to 0 because they're balanced. Okay. And we'll do the same thing we did in the last problem. Fn minus Fg is equal to 0. We do this because Fn is pointed upward and Fg is pointed downward, so they subtract from each other. Add Fg to both sides, and we find that the normal force is equal to the weight of the box. And we can obviously take that one step further, and we can say, all right, well, Fn is equal to mass times acceleration due to gravity. And now we can go ahead and plug in these numbers, which is going to be 0.5 kilograms times 10 meters per second squared. And we find that the normal force, which is equal to the weight of the box, is equal to 5 newtons. Okay. 5 newtons is the value for both the weight of the box and the normal force acting on the box here. All right, now we're going to move over to our horizontal forces. These forces are also balanced, so we will set it equal to 0. I know they're balanced because the box is moving at a constant velocity. So the applied force, which is pointed to the right, minus the frictional force, which is pointed to the left, is equal to 0. Okay. Now, I go ahead and rearrange this. The applied force will now be equal to the frictional force. We can show that if you add the frictional force to each side. And the nice thing here is that it already told me that the applied force is equal to 2.4 newtons in the question prompt that I've highlighted in green. And that means that that must also be the value of the frictional force that is acting against it. Whether that's a realistic number or not is another conversation for another day. But that is a pretty simple. Don't really even have to do a calculation there. Now, in the future, what might happen is I might give you the equation for friction, which includes the coefficient of friction, which is a number I would have to give you, and you would have to use the normal force to then calculate the frictional force, and then I would actually ask you to solve for the applied force instead. So this could be taken, another step further. So that's just a little bit of an introduction into how we're going to be doing the math problems with the free body diagrams and how the net force equations work into that. So we will expand on this later.